Have you ever looked at a piece of software and just wondered, what's really going on in there? Past that shiny user interface, there's a whole other world of code. Well, that's where reverse engineering comes in. It's our key to unlocking that world and finding out a program's deepest secrets. Today, we're going to explore this skill by breaking it all down into 5 distinct levels, starting from the basics and going all the way up to some real-world bug hunting.
Every piece of software, from a simple app on your phone to a nasty piece of malware, has a story to tell, if you know how to listen. So the fundamental question for a reverse engineer is always this: what does this program actually do, and how in the world does it do it? So here's the game plan. We're going to tackle this by climbing a ladder, 5 levels in total. We'll start with the absolute basics, then move up to more powerful techniques, and finally put it all together to see how the pros uncover a program's secrets, one level at a time.
Okay, so first things first. What is reverse engineering, really? Well, at its core, it's all about bridging a massive gap. The one between how a human thinks and writes code and how a computer actually operates.
Think about it. A programmer writes code with a clear goal in mind. They use descriptive variable names, they build logical functions, it all makes sense. But the computer, it sees none of that. It just gets a stream of raw, cryptic instructions. So reverse engineering is the art of working backward, taking those instructions and piecing together the original human idea.
And here's the challenge in a nutshell. On the left, you've got a simple human command in C code. We can all read that. But on the right, that's what the computer actually runs, a jumble of assembly instructions. Our entire job is to turn that confusing jumble on the right back into the clear, simple idea on the left.
All right, let's jump into level 1. This is the simplest and honestly a surprisingly effective technique. We're going to peek inside a real piece of malware and see what kind of secrets it just gives away for free.
You see, when a programmer writes code, they often leave behind little breadcrumbs of human-readable text. Things like error messages, web addresses, or commands. We call these strings, and they can be an absolute goldmine of information.
Check this out. This single line of text was pulled directly from that malware file. We haven't even looked at a single line of code yet, but we can already see what it's trying to do. It's clearly putting together an HTTP post request.
So, just by following these little text breadcrumbs, we've figured out its target, a Huawei home gateway. We know the type of a DAC, it's a command injection, which is just a fancy way of saying it's trying to trick the device into running a command it shouldn't. And we even have the IP address where it's downloading the next piece of malware. I mean, that's a massive head start, all from our simple level 1 technique.
But strings don't always tell you the whole story. Sometimes the real logic is buried in the code itself. So for our next level, we're going to tackle a crack me. It's basically a puzzle program protected by a password that we need to find. Okay, so we run the program, it asks for a password, we type something in, and nope, it just says bad kitty. Our goal is to find the right password. Now, looking at the strings, we can see there's a good kitty message in there somewhere, but we have no idea what input will actually trigger it. This is where static analysis comes in. It's the art of reading a program's code without ever hitting the run button. We use these incredibly powerful tools, like Ghidra or IDA, to take that confusing machine code and lift it into something that looks a lot more like C. This lets us actually follow the program's logic and see how it's checking the password. Sometimes, though, the logic you find in static analysis can get incredibly complicated. You've got loops, you've got math, it can be really tough to work through by hand. So, when just reading the code isn't enough, it's time to level up again and watch the code in action.
Welcome to dynamic analysis. Instead of just reading the code, we're going to run the program under a special kind of microscope called a debugger. This lets us see exactly what it's doing with our input, moment by moment.
And the key tool here is something called a breakpoint. We can basically tell the debugger, hey, stop right before the program checks my password. This freezes the program in time, letting us poke around and inspect its memory. We can literally just look at the spot in memory where the correct password is being stored for the comparison. And by doing that, we let the program do all the hard work for us. We set our breakpoint, took a peek at the program's memory, and bam, there it was, sitting right there, the correct password. No complex math needed on our part, we just caught it in the act.
But what happens when a problem is so complex that even watching it run is impractical? For the really tough challenges, we need to move away from observation and into pure mathematics. This is level 4, symbolic execution.
Now, the best way to think about this is that we're basically turning the entire program into a giant algebra problem. I know, it's a pretty wild idea, but it means we can let a computer do all the heavy lifting and just solve the puzzle for us. So here's the gist of it. Instead of giving the program a specific input like password, we give it a variable. Let's call it x. Then, a special engine explores every single path the program could possibly take. Finally, we just ask a math solver a simple question. Hey, what value of x will take me to the success message?
And here's what we get from a tricky crack me about trains. We didn't have to do any manual analysis, not a bit. We just pointed the symbolic execution engine at the program, told it we wanted to see that chugga-chugga choo-choo message, and it mathematically solved for the correct password. I mean, how cool is that?
Okay, time to put it all together. Level 5 is all about applying these different techniques to find real bugs in real software. And for our target, we're going after the firmware that runs on a cheap Wi-Fi router.
This is where our entire toolkit comes into play. First, we have to extract the firmware file. Then we use special tools to unpack the hidden file system that's buried inside it. From there, we can dig into the startup scripts to find the main program that runs the router's web server. And finally, we load that program into a tool like Ghidra and the hunt begins.
So, you see, level 5 isn't really one single technique. It's about the smart combination of everything we've learned so far, using strings to get our bearings, using static analysis to map out the code, and then dynamic analysis to confirm how it all works, all in the service of understanding a real-world device.
From malware and password puzzles, all the way to the firmware inside your router, reverse engineering gives you the power to really look under the hood of any software. So, now that you've seen the 5 levels of this powerful skill, what secrets would you want to uncover first?